opening day of this workshop. So to start the session, we have Professor Shankar from IMSC. So we'll have 25 minutes.
Can you hear me? Yeah, now I think. So the common thing is geometry, but it's not the geometry of space-time that I'll be talking about, but geometry that is there in the Hilbert space of states. So I thought that this would be an opportunity to sort of expose you to a different kind of geometry and also a chance to get some feedback from this community which has vast experience in geometry of space-time. So anyway, so this is my outline. That first, so this quantum geometry is a very old subject, which is almost as old as quantum mechanics. So I'll just initially review what is required for my purpose from that field, what you mean by what geometry in Hilbert space. Then talk about how it's applied to condensed matter physics. So it's the simplest context is in terms of so-called tight binding models. So I'll describe that. Those are just lattice models. And then describe what we mean by the shape, how you can ascribe a shape to a ground state of an insulator or ground state of a many particle state. And then finally, if there's time, some work that we've been doing on these issues. So in condensed matter physics, the whole activity has been motivated by these two phenomena, the quantum Hall effect and the discovery of high TC superconductors. Both these things were discovered in the 80s. And so the quantum Hall phenomena was very striking because of the extremely sharply well-defined value of a physically measured quantity, that is the Hall conductivity. So much so that the quantum Hall value has become the standard for the ohm today. It's then high TC superconductivity, the theorists find the normal phase of the high TC superconductors actually much more interesting than the superconducting phase itself, because that is a sort of very unusual kind of metal. It breaks down the paradigms of solid state physics, that is Fermi liquid theory. So people call it a strange metal, and it's believed that it's characterized by fractional quantum quasi-particles. So fractional charges, fractional statistics, etc., they occur in both these systems. And so ideas of applying topology came to, I mean, why is the quantum Hall thing such a robust quantity, sample independent, completely material independent, you get the same thing. So it's something that is so robust people try to explain it by identifying it with some topological invariant. And this is how the field started, and so they were trying to understand also the fractional statistics and charges, quantum numbers, etc. But there's also an underlying geometry under this, underlying this topology in some sense. I mean, after all, it's a topology of some object that has a shape also, and so that shape is the geometry. And it was started off in this context. It was started off by this paper by Berry, or the Berry phase. Then, well, according to the late Professor Ramseshan, this was the phase that launched 1,000 scripts. So many thousand scripts later, there was a lot of confusion initially. It was initially Berry posed it as a time evolution, a phase picked up during adiabatic time evolution. But there was a lot of work after that. Things got clarified, and according to me, when the dust settles, this is a most logically exposed paper where they talk about this phase as purely in terms of quantum kinematics. That has nothing to do with Hamiltonian time dependence, etc., time evolution, etc., but just the structure of the Hilbert space or physical space of states at some point of time. So I'll be following this thing. So let's start at the beginning. So physical state in quantum mechanics is a ray in Hilbert space, which means that it's not a vector, the vectors in Hilbert space and physical states, there's a many-to-one correspondence. Any psi and any complex number multiplied by things stands for the same state. So what is in one-to-one correspondence with physical states are the so-called pure state density matrices. You can see this quantity, if you multiply by a constant, it's invariant. And so then if you construct out of these density matrices invariance in the Hilbert space, so you can take n points in the Hilbert space and construct this quantity, which is this equal to just the trace of these corresponding, what do you call it, pure state density matrices. And these are actually what you call invariant. In the invariant under, if you multiply each of these by a phase, each state by a phase, they all cancel each other. And so it's a physically, in principle, a physically observable quantity, just a function of the physical state. So now you can define a distance using these these physical quantities. So this is just the second Bargmann. So these are called Bargmann invariants. So this is the second Bargmann invariant, psi 1, psi 2, psi 2, psi 1. And you can, this is a definition of a distance between these two states. You can show that this satisfies the triangle inequality, so it's a good definition of the distance. And if you take the third Bargmann invariant, that is rho 1, rho 2, rho 3, this is a complex quantity in general and it has a phase. So this phase was identified with the Berry phase or Pancharatnam Berry phase. Pancharatnam had discovered the same thing in the context of optics. So this was the work of Simon and Mukunda in that paper. They showed that this is a good way to think about the Berry phase. That it's, so you can take any path in Hilbert space, I mean go psi 1, psi 2, psi 3, go up to psi n, construct this quantity, and the phase of this quantity is exactly what would call the Berry phase. Now you have a distance and you have a defect angle. So you can construct a metric, a distance that satisfies the triangle inequality. So you can construct a metric by looking at 2 points close by. So look at some subspace of the rays parameterized by something, n parameters, and look at two nearby states, and you can define a metric on the parameter space, which corresponds to the distance between these two neighboring points in the Hilbert space. And this was again defined long ago. This is called the Fubini's 2D metric. Then you can, from this phase, I mean the geometric phase, you can look at three nearby points that form a small triangle and define a curvature that passes, I mean, you can think of some fictitious magnetic flux, passing through that triangle. And when the triangle becomes very small, you can define actually an antisymmetric tensor, which the same thing. So this is the Berry phase, and the vector potential corresponding to this is the Berry potential. And so there's a connection and there's a metric defined on this physical space of physical states. But let me just emphasize that this connection is not the corresponding to parallel transport of vectors. It's what you call the spin connection, which corresponds to how you parallel transport wave functions. So sometimes people put it together and call it a quantum geometric tensor, symmetric part, antisymmetric part, but I don't, this and this are physically very, very different, so I don't see the point in putting it together anyway. But okay, so that's all about, so all this was very general quantum mechanics, nothing to do with any particular system. Now let me come down to systems that condensed matter people are interested in. So these are so-called tight binding models. So you have a lattice in any number of dimensions, and you assume that all your electrons are tightly bound to the lattice sites. So they can just hop from lattice site to lattice site, and there's an amplitude for hopping from ith site to jth site, and you assume a translationally invariant amplitude, and this is the Hamiltonian. So this creates, annihilates an electron at the Bravais lattice site J, and each, it's not, each Bravais lattice, there's a lot of sublattices, which are labeled by this alpha, and so this is the most general form of a lattice you can have. Now you can go to Fourier transform, Bloch's theorem or whatever, and go to the K space. So because of the lattice structure, the momentum space is always periodic. Physically, that means that momentum is conserved only up to a reciprocal lattice vector, because translation symmetry is broken by the lattice. So these are what are called quasi momenta. And since this periodicity is there, the Brillouin zone is always topologically a torus. Shape might be anything, that depends on the shape of the original lattice, but topologically it's always a torus. And so you can write down the Hamiltonian in momentum space, which is completely decoupled between the different modes of the different momenta. So then to solve the non-interacting problem is easy, but you can define a set of eigenstates at each point in the Brillouin zone. You have a set of eigenstates. If there are n sublattices, this is an n by n matrix, so there are n eigenvalues, and it corresponds to n electronic bands. So, so now for each k, you have a density matrix corresponding. So take one of the bands, say the nth band, and for each k, you have a set of states parameterized by k. Set of single particle wave functions, this u of k, which are parameterized by k. So you go back to the previous definition. That is, so just in these definitions, replace psi by k. Is just think of it as a parameter, and you can define your metric and define a connection and the quantum geometric tensor. So k is the point, the Brillouin zone, the quasi momenta points are like your parameters. They are parameterizing some surface in the physical Hilbert space, and this is the metric induced by the Fubini-CD metric on that. So before going ahead, let me just give what are the physical manifestations of this metric and this Berry curvature. So first thing that started off all the interest in this was that this integral of the Berry curvature over the Brillouin zone happens to be a topological invariant it's called the Chern number. So it's completely independent of the details of the wave function. And in this paper, which was one of the reasons why Thouless got the Nobel Prize this time, they identified the Hall conductivity with this topological invariant. And that is what actually started off the whole huge activity in condensed matter, that you could do this. So, so this Hall conductivity being, it's a Hall conductivity very easily measured quantity. And so this is for the integrated K, which is what you call it, the the average B or the integrated B of the Brillouin zone. But the local B in K also has a nice meaning, and that was brought out by this paper by Ganesh Sundaram and New. So if you do semi-classical dynamics, so you look at waves in a crystal, and in the background of a very slowly varying potential, slowly varying magnetic and electric fields, slowly varying meaning slowly varying over the length scale of a lattice spacing. So they vary only over large distance of lattice spacing. And you look at semi-classical dynamics of wave packets under this approximation, and they derive this beautiful set of equations where k and so x and k are the centers of the wave packets. So beautifully symmetric between k and x. I always find this very fascinating. So this is the standard thing, that is the electric force, and this is the Lorentz force. This is the energy velocity, normal velocity being derivative dE by dk. And this Berry curvature gives you what is called the anomalous velocity. And so in this way, it's completely analogous to it being a magnetic field in momentum space. So even the B of k has this physical interpretation in this sense, at least in this semi-classical sense. Now, if the external magnetic field is 0, you can then do these things and identify this B of k with the Hall conductance. When you integrate over k, etc., you can. This is a nice way to derive the Thouless result, but approximate way in semi-classical approximation. The metric, not much physical meaning has been thing, except for this one, that it gives you a way to distinguish between insulators and metals. So as they say, the people who did this called it the sort of modern theory of the insulating state. So essentially, let me go to the next thing. The average metric, the metric integrated over the Brillouin zone, you can identify with the second moment of the pair correlation function. So this is the pair correlation function. Physically, it means that if you have a particle at 0, what is the probability of you having a particle at distance r away? So it gives you the structure of the quantum fluid, and it's an important quantity. And this is the second moment. So this average metric sort of gives you the shape of this pair correlation functions. Further, you can show that it is finite for this thing is finite for insulators and diverges for conductors. So that is why you can use it as a criterion for distinguishing between metal insulator. You can probe the metal insulator transition using this quantity, etc. And so now that there are at least some nice physical manifestations, let me talk a little bit more about how this gives you a sort of, you can visualize ascribe a shape to the ground state of a. So look at the ground state of some insulator, say, where all the one band is completely occupied and all the other bands are empty. So this represents a state, empty state with no electrons in it. Then you create, you fill up all electrons with for every point in the Brillouin zone with the wave function of the nth band. So this corresponds to an insulator with the leading order thing, no interaction. So there is no correlation between these two things. It's so-called what we call a mean field state. And so now each band, so you can see that each band gives you a mapping from, for every k, you have a wave function u of k. So it gives you a mapping from the Brillouin zone to the single particle Hilbert space. Now, we are considering tight binding models where basically there are n levels, where there are n sublattices. So your wave functions are n component vectors, they are simple. So the physical space is a complex projective space. And so you have a mapping from, for every k into this Cpn minus 1. So there's an image of this Brillouin zone in this Hilbert space. And then the Fubini-Sudi metric induces a metric on this surface, and that is what this GIK is. So k, that's why initially I titled this talk as metric in momentum space. I changed it because that's incorrect. The k's are just the parameters; they're more like local coordinates. The distance and the metric, etc., is in this image of the k in the Hilbert space, and that. So the metric actually, in some sense, gives you detailed information about the shape of that surface sitting inside the Hilbert space. So let me look at some examples where so two-band models are very easy things to visualize, because two-band models, there are two-component vectors at every k. And so two-component object, the projective Hilbert space is the sphere, and that is called the Bloch sphere in physics. So you can parameterize it explicitly by a theta and phi, and these correspond to the theta phi coordinates of the Bloch sphere. So if you look at graphene, so graphene is a hexagonal lattice with nearest neighbor hopping. I'm not going to go into the details of it, but as you probably know, it can be written, I mean, the quasi-particles satisfy a Dirac-like equation. So you can write the Hamiltonian to make it resemble the Dirac Hamiltonian, if you like, but these are more complicated functions. And I'm not going to go into explaining how, but it's easy to work out the eigenfunctions. And you can see that the entire Brillouin zone in this case is mapped onto the equator. So so this, as I said, these are the form. When you solve for the eigenfunctions of this, theta k is, for all k is equal to pi by 2, which means it's on the equator. So this mapping from the Brillouin zone to the physical Hilbert space can be many to one. It's not necessarily, and this explicitly shows it. So the whole torus, the two-dimensional system, so the Brillouin zone is a two-dimensional torus, and that is getting mapped onto a circle. Then when you put a staggered potential, so there are two sublattices, I mean, in the honeycomb lattice. you put a local potential which is different in the two of them. That is like adding a mass term in the Dirac equation. And then you can work out that the band, the Brillouin zone is mapped onto the northern hemisphere, one hemisphere alone. So it's a closed surface in the sense that it wraps around the northern hemisphere once, then it wraps around the other way again. And then you come to this Haldane model. So this was a very famous model. This is actually probably one of the reasons why he was given the Nobel Prize this time. So it was a model where, okay, let me, it added a more complicated kind of mass term. Yes. Yes. It's a positive and negative energy. So E plus, I mean, plus and minus E. So this thing has the eigenvalues come in pairs, plus and minus E, like the Dirac equation. And these are the two wave functions corresponding to it. So when I'm talking about one band fill, I'll be filling only positive energy or only negative energy, leaving the other one empty. So here, when the Brillouin zone completely wraps around the Bloch sphere. So here, when you calculate the Chern invariant, that turns out to be the winding number of this map, and that comes out to be 1. So this model is a very famous toy model, which gives you a case of Hall conductivity without a magnetic field. So it was what you call this quantum geometry, this Berry phase can be induced by purely band effects. You just have to break parity symmetry, and you can get this. Okay, so let me quickly go through. I have just 5 minutes left. So we've been exploring this a little bit. So we've been looking at this system, which is so-called Hofstadter problem, where you have a lattice and a magnetic field together. So there are two length scales in this problem. One is the lattice spacing, and the other is the so-called magnetic length. When these two are comparable, all types of interesting things happen. So I'll won't go through too much of the details. So we analyze it using mean field theory, which is a simplest approximation that you can do. And the thing is, we will search for translation and rotational symmetry breaking phases. So what we find is there are transitions. At some point, the initial point is completely symmetric phase, with the system having all the symmetries of the lattice. Oh, let me just go through one of the things again. Yes, so this has non-trivial Hall conductivity. There is a magnetic field which induces it. So when one band is filled, the Hall conductivity is -1. When two bands are filled, the Hall conductivity is +1. And at the half filling case, the Hall conductivity is 0. Why I came back to this was that the phase transitions we find change the Hall conductivity. So these are actually what are called topological phase transitions. So there's a first order transition at this point, which goes from the symmetric phase to a phase with broken translation and rotation symmetry. And it's accompanied by a change in the Hall conductivity. So it's a topological first order transition. Then after some time over here, there's another transition to a phase where inversion symmetry is also broken, and the system develops an electric dipole moment, spontaneous electric dipole moment. No, no. So these systems nowadays, there are experiments which can access this region, but the physical, so these are the Moire patterns on graphene, where you can make super lattices with much larger lattice spacing, get to this region. But the interaction you cannot tune, because graphene is graphene, electrons are electrons. So it happens to be in the symmetric phase. Now, so the hope is the theorists, the condensed matter theorists, what do you call it? Cold atoms, anything is supposed to be realizable. So maybe they can, but so far, no, it's not. But anyway, you can see the changes. So this I plotted the metric, the average metric, the trace of the average metric is what we plot over here. In the symmetric phase, so this 3 guys repeating reflects the translation symmetry of the original lattice. So then it drastically, the ground state shape drastically changes. So you can see that the metric drastically changes. Then again in the second transition, this inversion symmetry is broken, and that again reflects in the metric. So just to say that this is a good thing to monitor if you want to look at phase transitions. So you can also, this is again the same thing, we plotted the two eigenvalues of the thing. So this gives you the length scale of that localization of the correlation functions, and this gives you the measure of the anisotropy of the metric. And so there's a sharp jump, there's a first order transition, then it sort of constantly the anisotropy increases, length scale decreases of the pair correlations. So finally, let me finish. So we are planning to go ahead with this. But this was the first paper where, at least to our knowledge, that we could dig out, where this connection was made to this thing. And so this is the way, so the paper is about something else, localized Wannier tensor. They are looking at this localization tensor, pair correlation functions, etc. And say it is amusing to note that reference ideas of, so this is where the metric and Berry curvature were discussed, that, and then the whole thing is gone into an appendix. Now, at the moment, I can only again still say it's amusing to note we have not gone very far from there. See, the no dramatic applications of these ideas have come so far. It's true that, of course, the New Sundaram thing and anomalous Hall, this thing was there. Then it's a new way of characterizing insulators, but it didn't give any new calculation technique or anything. People have been looking, you can look at conductivity. You don't have to look at the metric. And conductivity is non-equilibrium quantity, this quantity is static. So you can nitpick a bit, but it's this tantalizing kind of thing that it's a nice, beautiful concept. So you feel like it's surely worth exploring and it'll give you something. But so far, this is, I think, in my opinion, this is the sort of status at the moment. So we are trying to understand this going beyond mean field theory. All what I defined was for non-interacting electrons. And so the only way what is there in the market to generalize to interacting system is that you use the Green's functions. Then the zero frequency Green's function happens to be, you can show it's a Hermitian operator. So you can, the inverse of the zero frequency thing you can define as an effective Hamiltonian. For the non-interacting case, it is indeed the single particle Hamiltonian. And then you can just take those eigenfunctions and do all the maths that one did earlier. But this is not very satisfying to us because there's no geometric picture behind it. And the true interacting state is far from being the mean field interacting state of this effective Hamiltonian. So there are questions there that we are probing. And so that's all. Thank you for your attention.
Full of questions?
Yeah, I have possibly one comment and a question. You know, the interplay between condensed matter physics and quantum field theory is something which we are all fascinated by. And there is give and take on both sides. For example, the Wilsonian renormalization group is the only way you can understand quantum field theory.
Yes.
And similarly, at least from my perspective, if you want to understand fractional quantum Hall effect, I find the field theoretic thing to be
Yes.
a lot easier than the microscopic description. But this is my comment, and it is something fascinating, and I think we are missing something. I mean, why the unreasonable effectiveness of quantum field theory in condensed matter physics is something which I don't know whether you have something to add, but that was my comment. The question is that, do you know any case where a quantum field theory method was used, and at the end you predicted something which we could check in the lab? That is, it is always after the fact. Somebody finds fractional quantum Hall effect could have been predicted by quantum field theory. We missed it. After it came, then we came up with an interpretation for that. Anyons is probably comes close to it, but other than that, I don't know of any example, including ADS, CFT correspondence, etc., where a new result was predicted using field theory and then got verified in the lab. Which is very strange because people keep talking about how do you verify quantum gravity, etc. We haven't even verified the application of quantum field theory to condensed matter physics in a predictable way or falsifiable way. That is something which probably you would like to comment on.
Well, I don't know field theory as such, but classic example is the Feynman diagram technique, which developed in quantum field theory, that led to BCS. I mean, the electron-electron effective. That was not a prediction of superconductivity, yes.
And say that if you heat this metal to this thing, it will do something.
Yes, but you see, to me, many body physics and quantum field theory are not very different.
That's right.
So when you predict something using many body theories, it is quantum field
It is
theory.
okay, that is the attitude
mean,
you would take. Yeah. Oh, okay. Well, my other interest is merely to ask whether anyone has written down the Einstein tensor for this metric and put it to 0 and saw what happened.
No.
Yeah.
No.
That's
So
an obvious
yes.
thing to do, right? You know, so,
No, so
or
can we get these things as a
exactly. So
solution to some equation of
right.
motion?
So given the metric, how far can you go? And then do you have a Lagrangian for the metric and, consistent with all symmetries? How does the coupling constants run?
And this answer is clear no.
Okay.
Nobody has done. And it's surely worthwhile. Sorry, we can.
Riemann tensor you can write.
We can write, but nobody has explored it to my knowledge.
No, I thought if you write the Riemann tensor, then formally you can construct the Einstein
Yes.
tensor. And
So, okay, for example, for this Haldane model, it's a sphere. So, it's a constant curvature. We know, I mean, you need to go beyond 2D. Yes, 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 yes.
Any further questions?
In your eigenfunction,
Yes.
you have, in the lower component, you have phi term, which is px by py or something, but not in the upper term. Yeah, this is cos theta, only theta dependent, and that is that
So this
tan
is,
phi.
you
This
can
is parity.
yeah, so you can push the phase up to either of these two components.
Yeah. And
So
that
it's just a convention that I've chosen the phase to be in the lower component. You can write it as e to the power I phi by 2, e to the power minus I phi by 2 here.
Yeah,
Because that's just
that
a
I know.
total phase to the
But
west.
does it break something, some parity symmetry or
No,
something?
no, it's just my convention of way I've written it looks asymmetric between the top and bottom components. It can be made symmetric.
Okay, so let's thank the speaker once again. Hello.